Vesper, I want to make it as simple as possible. So I'm not going to go into a big detailed discussion on Vesper theory. That's been done in 1210, 1220, and 12, maybe even 1200. If we look at the different groups, so first some of the groups of the day, the first group is the AX2 group, or what we would call group 2. Again, the A just stands for a central atom. And if you're looking at a central atom, a carbon within a longer chain structure can be a central atom for that given point. Or a nitrogen at a given point, and an amine can be a central atom, even though it's part of a longer group, it can be a central atom if we focus as that group as just some hard thing hanging off of it, right? Okay. So this holds true for all of these organic molecules that we've been looking at, that this central atom A is probably going to be for us carbon most of the time, sometimes nitrogen, sometimes oxygen, and very seldom sulfur in this class we'll see as a central atom. But those are the most common, okay? The AX2 refers to that you have some sort of central atom with two ligands, two other atoms attached to it. How does one carbon atom or one group have two other ligands? Well, it has to have carbon to something to something. Well, in order to have something to something, we know that carbon has to fulfill its octet. And does carbon like to have unshared pair of electrons? Especially two unshared pair of electrons. That's not a common bonding pattern, so what would be the more common bonding pattern would be something like this, right? Okay, whether it's carbon or oxygen on the side, the simplest model would be carbon dioxide, right? With two oxygens over here. And we can see an AX2. The AX2 is linear. The AX2 is also, the central atom is sp hybridized. So we know that this involves sp hybridization for that group 2 structure. Okay, that's the only way that we can explain what? 2 sigma bonds and 2 pi bonds. That's the only way we can't explain 2 pi bonds in any other way. The only way you form 1 pi bond is have 2 atomic p orbitals that can overlap, right? If to explain a second one, we have to have an additional p atomic orbital to overlap as well. So in order to have 2 available atomic p orbitals, the only way that's possible is to have an sp hybridization situation. Okay? So then we can go now to the group 3, which would be just AX3. Okay? Or we could have an AX2E. Now the E just represents, well, it's an unshared pair of electrons. So we could either have 3 ligands or 2 ligands with 1 unshared pair of electrons. Okay, simple enough. This is the group 3, and to show one of these, I could just do a simple structure like this. I'll do formaldehyde. Formaldehyde is a very simple compound. This would be my central atom, having 3 ligands attached to it, which I have how many sigma bonds? And 1 pi bond. Okay. How can I explain that 1 pi bond? What must be the hybridization of these atoms involved in that pi bond? It must be sp2. So it must be sp2 hybridization. And you can give other models with unshared pair of electrons. There's examples with nitrogen and so forth. Nitrogen and oxygen. Let's go to, what would be the shape of this thing? This one we know is going to be linear. There's no other way of putting that together. What would be the shape of this one right here? This one would be trigonal planar. Okay, so that's trigonal planar. Try to keep that as big as possible for you in the back there. What happens if you have an unshared pair of electrons in this case, though? If it's some unusual species that has, let's see if I can pull up an example. These are kind of unusual critters. Water is not a good example. I can find another good example here. That's an SP situation. These are kind of unusual situations. You would have something like a nitrogen double bonded to an oxygen, bonded to another oxygen with an unshared pair of electrons here in some sort of positive charge. Something kind of weird like this. Oh, no, I have a positive charge here. But that's the thing. So I'd have 3 bonds, and I'd have some sort of weird unshared pair of electrons. In this case, the structure would be bent. So this would be a bent structure. But the hybridization of the central atom would still be sp2. So how does that account for this thing right here? Not the second p orbital, because you don't have 2 available p orbitals in sp2, you only have 1. So where are they located? We have 2 sigma bonds, so that accounts for 2 of the sp hybrid orbitals. This must be held in another sp hybrid orbital, because there's 3 sp hybrid orbitals. So that unshared pair of electrons is out in a lobe of an sp hybrid, okay? Because this pi bond involves the other lone atomic p orbital. Is everyone understanding this? I know some of you are like, what the heck is he doing? And others are nodding like, oh yeah, this is cool. Yeah,
2 p orbitals that are taken out.
Alright, let's go on to group 4 then. Group 4 starts with AX4, AX3E, AX2E2. Let's give an example. The simplest example of an AX4 would be something like CH4 or CCl4. Both of these with the carbon as the central atom and chlorine atoms as the surrounding or the peripheral atoms, in this case being hydrogen. We know that in this case, all of these hybridization must be due to an sp3 situation. So these are sp3 type models. Okay. And in this case, we have 4 ligands around the central carbon. So if I have something like CH3, C, H, H, CH3, this being the central carbon right here, that is an H right there, sorry. This being the central carbon here, if I have 4 groups around it, this represents an AX4. It doesn't matter what those groups are, whether they're these, we call them methyl groups, whether these methyl groups, whether they're hydrogens, it doesn't matter, right? So it has 4 groups. What's the geometry around that central core there? Tetrahedral, because we know it's sp3, it has to be tetrahedral geometry. What happens if we have an AX, a situation where we have this now? The shape of this thing is trigonal pyramidal. It's not planar. Now, why is this one not planar? Because the unshared pair of electrons on top have an influence on those other orbits. These are still held in some sort of orbit. What type of orbit are these held in? They have to be in a hybrid orbital, right? Okay, we don't have a lone atomic p orbital there in this case. So these are held in some sort of sp3 they're pushing down. So this has some sort of trigonal pyramidal structure. One of the simplest compounds for this really is ammonia. It's a really good example of a situation where you have an AX3, so here's A with its 3 ligands and an unshared pair of electrons. It's definitely trigonal planar. And there's a lot of spectroscopic analysis on these molecules suggesting they do have these shapes. Okay. Alright. What is another one here? You notice that this has the same basic core as a tetrahedron. All we did was we just removed something. We just took one of the ligands off and left it as a pair of electrons. And you can't see electrons above this. When you look at the molecule, it looks just like there's empty space up there, right? But they're still there and they're influencing these guys and pushing down on them, so that's why it looks like this. It still has the basic core structure of an sp3 hybrid.
So did you say both those were trigonal pyramidal? No, one is trigonal planar.
No, the one up above is trigonal these are trigonal pyramidal, both of these
Those two
are
are?
pyramidal. This one up here is trigonal planar because this is a different situation.
Okay.
This involves a pi bond that holds things flat. Remember, I gave you some examples yesterday where that structure is flat. But that was in the sp2 hybridization, not the sp3 hybridization.
Yeah. Okay.
Got it?
Yep.
You notice that this is a little bit simpler than Gen Chem as well. We don't go on into any of the sp3b hybridization situations, right? We just have to worry about these guys right here. What's in a good example of this one right here? AX2E2. Water. That's a really good example of this one, right? So if we take oxygen with its hydrogen and an two unshared pairs, this makes a very good example of an AX2E2. An AX2E2 that we know that the central atom is still sp3 hybridized for the oxygen, and those two unshared pairs are held in sp hybrid orbitals, and the overall structure of this would be, again, bent or angular. Either way, it doesn't matter if you call it bent or angular, both of those are proper descriptions of that molecule. So we see two bent situations, or angular. One is the AX2E or the AX2E2. We have trigonal pyramidal, we have tetrahedral, and then we have trigonal planar, and then we have linear models. And these hold true for all of the organic molecules that you'll see in this semester and the next semester.
In the two cases with the bend, do we need to know about like the kind of angle between those?
No, the angles are sometimes different depending on the influence. Like water, the angle is about 105 degrees. So they know some of these angles, and they know that this one is a little bit wider angle because there's only one unshared pair of electrons, but you don't have to memorize any angles. You just have to know that they're in a bent position. Okay. All right. Any other questions? Okay. The true tetrahedron, this brings up a good question though, a good point. A true tetrahedron has the angles between each of the groups here is 109.5 degrees. So that seems to be the perfect angle for a tetrahedron. This doesn't have a perfect tetrahedral angle between these two. They've somehow moved down a little bit, they're squished down, so these must have a pretty good influence in pushing them down a little tighter than they would naturally be in 109.5 degrees. Okay. So everyone got this down? Very important. Okay. All right. Now it gets a little harder. Let's throw the organic chemistry into it now. Alright, now I'm going to point out one thing that's something that might confuse some students. I don't know why it does, but it sometimes does. Most of the time I'll write my C here and put my hydrogens to the left of it. In the book you might see CH3 and C, something like that, where they just put them to the right of the symbol. The reason I move mine out is to imply that the carbons are connected together and not the hydrogens. So don't let that bother you. If you see this in the book, just note that these hydrogens should be out and the carbons are actually connected together. That's just a clarification point. Let's take a look now at these two molecules right here, or two representations of the same molecule. These are resonance diagrams of the same thing. If you look at just this resonance structure right here, what type of hybridization would you consider for the central carbon atom? Just looking at that, what would you say?
sp2.
Could it be sp3?
SP2.
Well, what about about this one right up here that has 4 groups around it? Could this be
It could be.
4 sp hybrid orbitals with 3 unshaped pairs and 3 of those sp hybrids, and then the 4th one forming a sigma bond here? Okay, now this is a little bit of a tougher situation when you're looking at this guy right here, trying to define its hybridization pattern. What you have to do is look for any resonance structures that might be other contributors. So then we look at its other resonance structure, which is this one, and we say, oh, that's a significant resonance structure. In fact, this one is probably more significant than this one, because this one applies charges to these species, plus this one is electron deficient, right, and it doesn't have a complete octet. So once we can define other resonance structures that show us that there's a double bond present, then we can now say it looks like both the carbon and oxygen are sp2 hybridized and not sp3 hybridized. Does that make sense? Okay, so even this species, this resonance hybrid, or not this one, the resonance hybrid between these two, O minus, delta plus, CH3, CH3. This must have what shape to the molecule? It must be trigonoplanar. It looks like it's an AX3 group, right? An AX3. It looks like there's some sort of sp hybridization between these 2 species right here. And this guy right here looks like it is a flat planar molecule. Alright. So resonance can be tricky. There's one in your book I want to bring up here. It's a CH2, NH2, oh, this be 2. And then they put a plus out here and they said, okay, what's the hybridization around the carbon and nitrogen in this molecule? Okay, stretch. What the heck does this thing look like in the first place? So now we have to put it back together. Putting it back together, requires a little bit of common sense here in looking at this plus charge has to go to one of these atoms. Could the plus go to a nitrogen just as well as a carbon? The answer would be yes, but a nitrogen would have to have how many groups in order to be charged with a plus? 4, right? And it doesn't look like it has 4 because 2 of these hydrogens are so, or they put them on this side of the formula for a reason, and they split them out from this side for a reason. They didn't say NH, they didn't say C, NH4. So there has to be a reason why they put 2 over here and 2 over here, right? Moreover, how are you going to put this thing together if you put a carbon to a nitrogen with 4 ligands out here? And you're thinking, what the heck are you going to do with that thing? Okay? That doesn't make sense at all according to our bonding patterns. So we have to use a little bit of common sense in the way we put this together. It looks like this is, an attempt has been made to say that there are 2 hydrogens to 1 carbon atom, and that somehow the carbon is connected to the nitrogen, and there are 2 hydrogen atoms to the nitrogen as well. Something's got to be like this. Okay? Now I put it back together and I say, according to my common bonding patterns, they didn't give me any more information other than there's a positive charge in here. Should I send a positive charge here, or what do I do? The way it's drawn, I could put this positive charge on here, but I know that something else is missing here, it looks like.
A lone pair.
A lone pair, and that would be on the nitrogen right there. But the nitrogen is not charged in this situation. It's got 3 bonds and so forth. Okay. So I look at that and I say, okay, that's one resonance structure. Can we draw another resonance structure to give us a handle on what the hybridization looks like?
Yes.
Could we move this pair down into here and draw it like this? And that moves the charge to the nitrogen. We just share the charge over here, but that doesn't seem to bother us, right? As far as our common bonding pattern. And then I look at this and I say, this looks like a reasonable resonance structure because this one was actually, didn't have a complete octet on the positive charge. This one has a complete octet all over with the positive charge. This one is probably the major contributor, and it looks like the carbon and nitrogen are, what hybridization? How many groups? This is an A, X, 3. What is that one right there? AX3. What would be the hybridization on an AX3? These are both sp2 hybrids. okay? So if you see something like this on a quiz, you need to draw it out. A lot of students like to skip steps. What steps did I take? I looked at this and said, what the heck does that mean first? Then I tried to figure it out in my head and say, what does it mean logically to me the way they have it drawn here? Where does this positive charge go in terms of my formal charges that I can apply to a given atom and along with the common bonding patterns? I put together this. That seemed reasonable to start with. Then what did I do? Are there any other resonance structures that would contribute to this thing to make it look a little nicer?
So would the geometry just be a trigonal planar then?
Around each of these, but what's the geometry of this whole thing? Is this flat planar? We know that all of these hydrogen atoms are in the same plane. Okay, so it's flat planar, but these around each of those atoms, that's trigonal planar, that's trigonal planar.
But as a whole would be a flat planar?
Uh-huh. So it would be something like this. Okay? Once you have a double bond between two species, here's a group, here's a group, here's a group, here's a group. If I lay it flat, you can see that they're all within the same plane. Let's I can emphasize this a little bit better. Pulling up those groups. You can think of one of these, I'm not going to try to change the color of this right now, but think of one of these as being a nitrogen, and one of those being a carbon, and we have a double bond characteristic between the two. See how that's flat and planar? The whole thing. But around around that carbon atom I have trigonal planar, around that carbon atom, or around the nitrogen, if I were nitrogen, I'd have a trigonal planar as well. The whole molecule is flat planar right there. Now, if this were part of a longer structure, it's only flat planar in this region of the molecule. The rest of the molecule could have tetrahedral structure to it. Okay?
When you want us to draw the hybrid,
Sometimes I might ask you for the hybrid, other times I would just ask you what is the sp hybridization, and I wouldn't say draw the hybrid, but you'd have to know to draw these resonance structures in order to calculate or figure out what type of hybridization takes place. It's somewhat obvious, although if you look at this one looks like an, right? If I look at that one right there, and then this one looks like an AX3, so I'm getting a different message by just looking at this one resonance structure, this one resonance form, but that's not the entire molecule.
So the formal charge over N is positive, right?
And this, yeah,
So I remember how you said to figure out the formal charge, isn't it number of bonds minus unshared pair of electrons, well valence electrons minus number of bonds
minus 1/2 the shared electrons.
Yeah, so if you figure that out, is it equal to positive?
Yes, you have 4 bonds and no unshared pairs on nitrogen.
Four minus
so
zero
positive
minus
charge.
4 minus 0 minus
You can go back and look at your common bonding patterns. Anytime you have nitrogen with 4 bonds, no unshared is positively charged. You can go through the formal charges and figure that out, but that's what I did.
This is so important.
And is it nitrogen that you find in nature that's rarely negatively charged or positively charged?
Rarely negatively charged,
Two
but a lot of positive charge.
But if you take the
In carbon it's rarely negatively charged, right?
It's rarely negative and rarely positive, but it does go through those states.
that's what you add a bond,
Does.
you make a bond.
Let's just pretend that you're born an organic chemist genius and you just automatically put the bottom one. Do you lose points for not putting the top one? Like if you can draw it out, like if you draw
Oh, if you can jump from here to here?
yeah,
No,
you would just be, you'd be okay with that.
unless I asked you to draw all resonance forms.
Okay, then you'd have to add them.
Yeah, then you have to have the other one. If I just asked you for hybridization, you can sit there and say, eeny, meeny, miny, moe, SP3.
Okay,
Okay, and then you can move on and get it wrong,
right,
okay?
but you wanna, but you wouldn't lose points for not doing that middle resonance if you
No, if I just ask for hybridization, I want you to be able to identify it. The problem is that if you don't go through these steps, you might get it wrong, you might not. Okay? So I'm just showing you the steps. Okay. Any other questions?
No.
You mentioned flat planar, and normally on all the VSPR charts that I look at, it doesn't go that far in depth. Are there any other VSPR model like geometrical arrangements that we need to know?
Very good question, no, for this class. The only other ones we're gonna talk about are conformations and some configurations, but the overall geometries are the same. And then when we get into cyclic structures, there's gonna be some unique characteristics of cyclic structures, but they're just kind of variations of these things, okay?